so that you can check it out later.
Go for it.
So welcome to the San Francisco MySQL meetup. It's the first one of the year, 2015.
Woo!
That's pretty exciting. And I can't believe so many of you came, even though we changed the location at the last minute. But this is a really nice space. So we have to thank IFWE for being our location sponsor. And that's really great. It's such a nice. And then we have our typical sponsors. You know, Percona always gives us food. So we have to thank Percona for the pizza. And our other sponsors are O'Reilly and Lithium and Vendini. And who else am I leaving? Anybody off?
I can't think of
I
anybody
think
else.
that's all our sponsors. Next month, we're going to have someone come out and talk about tools. I've asked him to take his talk from a beginner talk to an intermediate. It's Ike, who's in our chat. I can't remember Ike's last name that David probably knows from Boston. Oh, what do you know? But anyway, somebody's coming out next month, and it'll be February the 11th. We'll be back on a Wednesday. We'll be back at Lithium. And it'll be great to come out. It will not be a beginning talk on Toolkit, so we need you all to show up and harass Ike and make sure he doesn't give us a beginning talk. And then tonight, I just feel really fortunate that I was chatting with Robert, trying to find out what he's doing now that Continuant was bought. And he told me he was working with Cassandra, and I said, oh my God, I've been looking for a Cassandra speaker. Do you have a talk you could do? And I tried to twist his arm for December. I'm really glad he said no, because I was too busy in December. And so now we have Robert here. And those of you that have been to many of his replication talks know that we can ask him hardcore questions, so please do, because the rest of us in the audience want to ask him the same questions. So never feel like your question is bad, no matter how simple. And I can't wait to hear this talk, so I'm going to hand this over to Robert.
Okay, thanks Aaron, thanks Mike. So it's a real pleasure to be here tonight. I have an initial question, which is, how many of you guys actually use Cassandra? Oh crap. So there's actually people in the audience who know about Cassandra. This could be bad for me. So the way that this talk got started was, I'm kind of pals with Tim Callahan, who's the VP of Engineering at Tokatech, and we both are kind of database nerds. And we decided to start this series where we're just comparing different database types. And because we know and love MySQL, we would start by saying, okay, we kind of know how MySQL works. So let's take that knowledge and see how we can use it to figure out other types of databases. So we started with a talk on MongoDB. That was good. It was a little bit boring, actually, because Mongo, in many ways, is very similar to MySQL. But we then decided to extend it to Cassandra. So Cassandra is a much more interesting topic because in many ways it's quite different from MySQL, but at the same time, as you look inside it, there are some surprising similarities. Moreover, if you know how MySQL works, you can ask the right sort of questions to teach yourself Cassandra and understand the ins and outs, and then be able to compare MySQL to Cassandra and decide which one to use in which case. So let me just jump in. A little bit about who we are. I'm a senior staff engineer now. I used to be the CEO of Continuant. We got acquired on October 28th. So I've been working with databases for a really long time. I started with something called M204, which was written and actually in production and very successful a long time before at least some of you guys were born. So it's been doing it for over 30 years. I'm working at VMware since the acquisition on database as a service. So VMware is building a public cloud. It's called vCloud Air. Very interesting piece of technology, and I'm responsible for a lot of the data management there. Tim, who is not here tonight but contributed fundamentally to this talk, is the VP of Engineering at Tokatech. He is a great database guy. So he's also very good on benchmarking. Has anybody seen any of Tim's talks? So he's really good. And I think that in addition to supplying a lot of great information and getting this talk off the ground, he kept me from backing out, because we did this for Percona Live. I had some stuff come up where if there had been any honorable way, I would have backed out of doing this talk. Fortunately, Tim was there and I committed to do it, so here it is today. So I owe Tim multiple dollars. So Cassandra, it's a pretty popular database, and this gives you an example. Just a few of the people that are using it. Netflix made a big commitment to it. In fact, I think they pulled a substantial fraction of their data that was originally running on MySQL. They're now running applications against Cassandra. But just a raft of other popular websites that are using it. Nest, you guys are familiar with Nest, the thermometer guys? They use Cassandra. In fact, if you talk to the data stacks folks, that's one of their favorite customers because they're really big and have a lot of data. And one of the things that Cassandra is really kind of famous for is it has very, very high performance writes. And we'll talk quite a bit about that, as well as linear scalability and high availability. And so by linear scalability, what we mean by that is as your data set grows, Cassandra will grow very easily to continue processing. And in fact, as you start to look at Cassandra, sort of as a newbie, one of the things that we did was we tried to pick what's something we really like about this database. And one of the things that's incredibly cool about Cassandra is that you can just run it. It's like MySQL. You can run it on commodity hardware. You don't have to do anything really special to build a high-performance system. But say you're running a Cassandra database and you've got your data spread across 4 machines, and you're starting to fill up. Well, what you can do is just rack a couple of new nodes, or you can allocate them in Amazon or in future vCloud Air, and you basically just install Cassandra, tell the new nodes where the existing Cassandra cluster is, let them join, and Cassandra will sort of auto-magically distribute the data out to the new nodes. This is incredibly cool, because if you have an application that's just sort of growing without bounds, you can just keep adding machines, and Cassandra will just use them automatically. This is a very, very cool feature. And for anybody who's for those of you who run MySQL, is anybody running a database that's over 1 terabyte? Okay, one. Anybody over 5 terabytes? Right, the biggest one I've worked with is about 8 to 9 terabytes. MySQL just basically hits a kind of a wall at some point. You just don't have, for example, enough memory to be able to process the data efficiently, because you're basically restricted to a single node. And you end up sort of going into your application, splitting it up into pieces, and sharding it across a bunch of nodes. Cassandra completely solves this problem. It just goes away. But there's a bad thing about Cassandra, and this is where we really start to dig in. So Cassandra has this thing called CQL. Get it? It's C, Cassandra query language. And you can dive in, and you can create a table, and there's a table food, and it looks an awful lot like MySQL. Those commands right there, I'm pretty sure if you type them into MySQL, they would just work. So you create tables, and it looks like you're using SQL, but the first thing you want to do is, hey, you got this table, you'd like to construct an index on it. So you make an index so that you can look up, so that you can link customer ID, order ID, and look up and use that to do efficient queries. And Cassandra just bombs out. And this is actually kind of a nice way of describing it, because Cassandra, the compiler just says, hey, I don't even know what you're talking about. And the basic problem is that Cassandra only supports indexes on a single column. And we'll dig into why that is. But so right as you dive in, you have this thing that looks like SQL, but it really isn't. So the question is, you've got a good thing, you've got a bad thing. So how can we take our knowledge of MySQL, kind of dig into how this thing works, and really get up to speed on what's going on? So the first thing we're going to do is explore the data model. And the big lesson here is this thing that they call CQL is not SQL. It looks kind of similar. It uses the same syntax, but it is very, very different beast. And the reason is that there's kind of different stuff underneath, a different organization of data. So let's just explore SQL. So originally when Cassandra was developed, it used a thrift RPC API, and apparently it was universally hated. I didn't really use Cassandra back then. By the time that I got to use Cassandra, they had sort of given up and decided in order to become popular, they needed to use SQL. So a lot of database designers have made exactly the same choice. So about version 8, they added CQL, and the basic idea, as you see, was to make you feel like you're dealing with something familiar. And so they created the SQL language, and in fact, what's interesting is all the other APIs that they use, they just kind of threw away. They're no longer really supported, they're no longer documented. The problem is that underneath, it's not really a relational database, so let's dig in. So it's SQL, but it doesn't do joins, for example. It doesn't have foreign keys. There's a long list, actually, of stuff that it doesn't do. And one of the things we'll focus on a little bit is indexes work completely differently from the way that they do in MySQL. So it looks like SQL, but it's got a bunch of differences. So the thing about SQL, or using the Cassandra's version of SQL, is that they put this sort of layer on top to give you easy access to your data, but it's really kind of different. And so what you have to do is think a little bit about, hey, what's going on underneath, and what is it that Cassandra is really going to do? And so one of the really big lessons that you get that you learn very quickly is you don't just toss data into Cassandra, because the idea, with MySQL, you can just create a bunch of tables and run queries on them. And when you don't like a query performance, you can add indexes, for example. So how many of you guys do query optimization? So you run explain, you say, okay, this thing's doing I need an index here because it's doing a table scan, or it could be doing a lookup. I can do a covering index, for example, so that I can, and the whole idea is that you're reducing the amount of data you have to process to get an answer. Well, Cassandra, because of the way that it organizes data, doesn't allow you to do that. So you have to do a lot of upfront thinking. So let's go in a little bit and talk about that. So, question? Did somebody say something?
I think it was just a shuffle. I regret it. We were just laughing.
Oh, okay. At this or the previous one?
This one.
There we go. Yeah, so this is definitely Cassandra. And one of the big things that are coming from MySQL is actually Cassandra. The more you get into it, you go through this period where you immediately think, hey, this is pretty easy because it's got SQL. Then you start to try it out and you get horribly confused because you don't understand what it's doing. And then you sort of break through that after a while and it starts to make sense. So in fact, coming from the relational world, here's some things that are really, that we're going to be focusing on that are actually pretty good. So Cassandra is built, and this is something I'm going to harp on for the next 45 minutes or so. Cassandra is built to solve a very, very different problem from what MySQL is designed to do. And at the end, I've got kind of a punchline where there's two applications that we can compare where Cassandra is really great for one and MySQL is really great for the other. So if you look at these guys here, so the relational databases have this big single point of failure problem, or SPOF problem. So Cassandra solves that problem. Cassandra also works across data center. Cassandra has linear scaling, but the data modeling is not so great. And this is a trade-off so that you can solve those first three problems. So thinking in terms of MySQL data, you go to Cassandra, you actually find some stuff that looks kind of similar. So Cassandra, in MySQL, we have a thing called a database. People who are not MySQL users would call it a schema. In Cassandra, it's a thing called a key space. So it's basically kind of a collection of tables. In Cassandra, they're called column families officially, but actually when you use CQL, you can just call them tables. They have primary keys. Those are used to look up rows in these tables. You have column names, and Cassandra has something pretty similar, but a little bit different. And then you can call them values, sort of, you can think of them as cells in a particular row. So Cassandra, as you look down this list, at first glance, this actually looks kind of similar. But as we dig into it, it's actually quite different underneath. So Cassandra is, how many of you have heard of big table? Okay, good. So how many of you have read the paper? Okay, we have two great people. So big table is a model for managing data that was developed at Google. And the use case that they were solving was, hey, I've got a web page, and that web page has a bunch of references to it, so I'd like to be able to index it by the name of the web page, so the URL. And then I'd like to have this tremendously long row that contains a bunch of arbitrary columns that describe that web page. So some of them might be sort of metadata about the web page. Some of the other columns might be references, sort of links to that web page. So it's a kind of funny data model, and the idea is that it uses these things that are sometimes called wide rows. And there's a row key, and then you have a bunch of different columns, and the columns can all be named differently. So each row can have a different set of column names, and you can actually have up to 2 billion of them. So this is not a relational model. In MySQL, you have a table, and you have like a primary key perhaps and a couple columns, and every row in that table is going to have exactly the same. Set of columns. Moreover, there's kind of a limit in MySQL, and I don't know what the current limit is, but anything over a couple hundred columns is starting to be very, very large, and you start to have a lot of performance problems. So big table is a completely different structure. It has another kind of interesting feature, which is the columns, within the rows, the columns are sorted. So for example, if you had a column named A, it would normally come before B. So this has some kind of interesting impacts that we'll see in just a minute. So we're already seeing a difference here that under the covers, Cassandra is actually quite different from the standard relational data model. So Cassandra actually has a pretty good type model. So we're used to dealing with types in MySQL, which are basically scalars. So, they're integers, they're varchars, they're blob or text or whatever, they're single values. Now, Cassandra actually has a richer set than this. So it's got the usual things, but it's actually got things like UUIDs or an INET variable, variant. So it's actually got some pretty, useful scalar data types. And we'll see some of the others in a minute. So in Cassandra, you can actually create just what we would call a static table that looks just like a MySQL table. So we go ahead and we create table users, and it has a primary key that's users. And when you do this, what this is doing, if you go and look inside the wide rows, they actually look kind of like a relational table. They've got the key, the user key, which is used to look it up. So Cassandra has a bunch of nodes, so it will go figure out where that user is. It'll go out to the node that contains it, and then it'll find the row and it'll look up the rest of the stuff. Now, there's kind of an interesting thing which we'll talk about more in the future of this talk, later in this talk. There's also a timestamp on every cell in the table, and what that does is it allows us to tell when that table was updated. Moreover, there's a thing called a TTL, which says how long should this data live. So we'll talk about that as well. So basically, the primary keys, when we look at these rows, there's a really fundamental difference here. In MySQL, you can ask a question like, fetch everybody who's, like if you have primary keys and you're just using integers, you can do a select where, for example, user, let's say it's, user is greater than Robert but less than Trevor, and it'll actually do a range. Well, Cassandra won't do that. It will only look up the keys. It doesn't do a range, and you'll see why that is in a bit. So there's some other differences here. It doesn't have sort of not null or varchar or anything like that. It's very easy to change the schema. That's actually a really good thing about Cassandra. You can just do an alter. It'll go ahead and make the change, and you don't have to stop your applications. There's no sort of going offline. So these static tables, they look kind of like what's going on in SQL. Some differences, like the fact you can't scan ranges of primary keys, but then also the ability in return to do schema changes without changing graphs. So is this making sense so far? Tell me if I need to go down, go up. I'm sort of a database nerd, so I really like this stuff. One really interesting thing about Cassandra is it doesn't do auto increment. And the reason is that in a distributed system, and remember we're storing data across a bunch of nodes. My examples show 4, 6, something like that, because that's how many I can draw easily on these slides. A real Cassandra cluster might have 100 nodes. So if you think about auto increment keys, you're going to have to, if you select the next number in an auto increment sequence, you're actually going to potentially have to ask every single node, hey, what's the highest number you've got? You'll have to have consensus, in other words. So you don't have typically use auto increment keys. So normally what you do in Cassandra is you use some sort of natural primary key, or you use a UUID. So UUID is a generated ID. It's random, it's pretty much guaranteed to be unique. And Cassandra will make one for you. So that's another difference from MySQL, and something that we're trading off because we're no longer sitting on one server, but in fact building a data processing system that it can expand to other nodes and more. So indexes. This is really kind of interesting. So Cassandra really doesn't do indexes, not in the way we think of them in MySQL. So there are a couple of options. They do have an index command, and so for example, we have this table of users. We can look up, we can create an index on state, and we can go find it. And that will create an index, but it's actually going to, as you'll see in a minute, it actually behaves quite differently. The other thing you can do is, if you think about, you ever think about how indexes are constructed? They really kind of invert data. In fact, that's sometimes a phrase that's used to describe what an index does. It says, hey, here's the value, and here's all the records it's found in. Well, if you think about that wide row that I showed you just a few minutes, that's an ideal structure for constructing an index. So you can, in fact, create a table yourself, make your own indexes in Cassandra, and this is a users by state table, which just links user and state. And so you have the primary key here, and you can quickly look these things up. So this is so in Cassandra, you really have two choices. If you want real flexibility in indexing, you can do it yourself. You can use the built-in indexes. There's some actually pretty good trade-offs between these two approaches. So, in general, people don't, it's not recommended to create secondary indexes in a lot of cases. The interesting thing about these indexes is they're actually maintained in chunks on each node. So all the data on a particular node, there's an index built for it on that node, but there's no global index. So when you ask Cassandra to make a secondary index for you and then you use it, Cassandra will go out and query every single node in the cluster to find the values. That's actually not so bad if it's just a couple nodes, but if there's 100, it could be really bad because maybe one of those guys doesn't respond quickly. We'll talk about that problem in a minute. So these indexes that Cassandra builds for you are actually maybe not so good. Now the cool thing, if you build that additional table the way I showed in the previous example, that because it's just the primary key value that we've constructed is going to be found on a single node. All the data in that row is going to be found on one node. Cassandra will pop out to a single server, get all the information, all the references from that index, and basically allow you to find them. But the problem is that it's then an application. It's like an application problem to make that index, to maintain it, and to use it. So it's kind of an interesting, really interesting contrast here. So in general, indexes that have very low selectivity. So for example, an index of male versus female, which is like in many database systems we represent as a bitmap. This is really bad in Cassandra. This is not something you want to index. Similarly, something that has very high selectivity, where you end up just getting a single row, that could be bad too, because especially if you have to go out to a bunch of, if you're using the built-in indexes, and you end up going out to 100 nodes to get that one row, that's really bad. So in general, what people often do is create the additional table, but you have to really think about what the index is doing before you create it. So one of the really powerful things is using these, really kind of leveraging these wide rows. And in Cassandra, Cassandra is a little bit tricky because the nomenclature has changed over time. And Cassandra is not super consistent. So these used to be called at one time dynamic tables. If you look in the documentation, you don't use this name anymore. But if you do something like the following, you can actually create a primary key that has two columns in it. And what Cassandra does in this case is the first part of the key, in this case the user, is called the partition key. And that actually goes and finds the wide row. And then if you look inside that row, what you'll see is it's then blocked out. It has additional sort of columns, where the column names, like ID1 and ID2, those are actually values. They're not column names. And then under that, they have the additional information, in this case, type and amount. This is a completely different structure from what we're used to in databases. Yes? Question?
Given your representations, can I understand that a row is all stored together in the same data block on the same device?
Yes, a row is stored in one place, exactly. That is correct. So, and that's very important. That what happens is that user, that what's called a partition key. So if you read the Cassandra documentation, that locates your wide row, and it's really used to look up the machine where that data exists, and then the entire row is fetched out. So, and we'll talk more about the behavior of these wide rows, because this is kind of the fundamental data structure inside Cassandra. So, so you have these wide rows, and when you do this is actually quite interesting, because those guys are sorted. The secondary and tertiary columns in the primary key, depending on how many you have, they're then stored in sorted order. So now you can do things like range queries, and you can do order bys. And you can have a lot of these, because Cassandra supports up to 2 billion of these columns. So this is a structure that you tend to lean on quite a bit when you build things in Cassandra. And if you think about it, where's an obvious case where this might be useful? Can anybody think of something where, if you go back to Nest, and this kind of gets, yes?
Time series?
Time series, yes, absolutely. That's like a real sweet spot for Cassandra. Exactly. So imagine you have your Nest thermometer, and it is secretly reporting the temperature inside your house or various settings. What it can do is there's a device ID, that would be a partition key, and then you have the timestamp that it actually took the measurement. That's the next column in your key, and it just sorts them by the timestamp value. So Cassandra is very good for time series, much better in many ways than MySQL is. So relationships. Well, so we don't have primary keys now, we don't have foreign keys. So these, so the normal way that you attack this by indexing, creating foreign keys and things like that, you don't do that in Cassandra. But one of the things that's kind of interesting that you can do is you can actually construct. What you tend to do is denormalizing, or various tricks around denormalizing. And this is kind of a trick here, where actually what we're doing is we're creating a primary key so that we can link department ID and department name as a single lookup. And so that's the key. And then it basically goes ahead and lists the employees who are in this particular department. So you tend to do these tricks where you actually build the structural relationships into your tables. Yes?
If you allow me a quick question, comment?
Yeah.
The
Yeah, and I'll get to the user-defined types in a minute. Yeah, I think this is actually actually user-defined types and actually the collection class is a really great feature of Cassandra. Time series data, I already mentioned that. So time series is very good within Cassandra. So here's a good example of where you have like a dashboard, and you have dashboard ID event time. So you're actually collecting a bunch of events associated with a particular dashboard in some application. And what's also interesting is there's this, Cassandra will allow you to play games with the sorting of the columns. This is actually not recommended according to the documentation, but by saying clustering order by, you can rank them in descending event time. So basically, when you scan the row, the most recent event will come out first. I think that actually has some performance impacts because you tend to have to shift the rows when you're updating, but it's handy if you want to enforce certain semantics. So, and that the slide kind of describes the advantages of that. There's another really cool feature. Actually, MongoDB has this feature as well, and it's time to live. So with time series, one of the things that you often get is if something happened, like you're thinking about, again, devices reporting information. If it happened in the last 3 days, you care about it, but beyond that, it's yesterday's news. So what you can do is you can actually do inserts where you specify a time to live on the data. And so this is an example of this. And let's see, 86,400. That sounds. Is that a day? Yeah. So it's about 24 hours. So basically, anything that insert right there is going to disappear magically after 24 hours. This is actually a very cool feature. Again, sort of canted toward time-sensitive data. So if the data just disappears, probably not quite after 24 hours. It's sort of whenever Cassandra gets around to it. But you don't have to have cron jobs to do this. It just is handled by Cassandra. Yes?
Is that easily adjusted, or is that an update to all your?
Actually, what's happening is it's specified as part of the insert. So once you've set it, I suppose you could go out and change it. What's interesting is that Cassandra doesn't give you terrifically good tools for messing with this TTL because it's not really part of the SQL semantics. It's like an extra field associated with the cell. At least that's been my experience. It's a little bit hard to look at though, actually, just to give you an example. But what you can do is change your app. And in fact, a lot of things with NoSQL databases in general, but Cassandra in particular, is if you don't like something, you're not going to twist the knob, you're typically going to change your application. And I'll show more examples of that shortly. So, other cool schema features. Yes, collection classes. I like these. I haven't used them, but as the gentleman over here correctly pointed out, these are very, very useful. So, they include maps, they include lists, sets. You can add your own. It's so here's an example. Let's see Tim's using a set here. So you can put a bunch of different values in. That's actually a pretty cool feature. So again, it's sort of this fundamental difference. We're used in MySQL to dealing with a single row, scalar values. In MySQL, you're actually thinking about, it's not so much a row. One of the ways that Cassandra people sometimes think about this is it is a hash, sort of the partition key, which then gives you an additional hash table, which is a bunch of key value pairs. So it's a much richer data structure that you're getting back from that partition key than a simple row. So that's a very useful feature. I also like the time to live quite a bit. So that's some of the basic data modeling differences. Does this make sense so far? Any questions? Okay. So the next part of this talk is to start to look inside Cassandra. And this gets into, as you start to look inside Cassandra, we've seen some of the sort of the functional differences between this CQL dialect and SQL that we know and love in MySQL. As you start to look into it, inside Cassandra, how it's storing data, how it's distributing data, you're going to begin to get into what I call life at the long tail. Does anybody know, are you guys familiar with that expression, the long tail? If you're not, there's a really wonderful talk at Recon 2013. It's sponsored by React, by Jeffrey Dean from Google. It's called The Tale at Scale. And it talks about the problems that you get in distributed systems. And the specific problem that they're circling around in that talk is that when you have a bunch of data spread across a bunch of nodes, you get some very interesting problems that don't exist when you have a single database instance. So for example, if you do something that requires you to scan all of the instances, you're basically vulnerable to the slowest instance. So if any one of those 100 is not responding, it will slow everything down. And in fact, the more nodes you get, in effect, the slower and slower things go. The slower and slower your applications go. So this Tale at Scale talk talks about that problem. And the reason I bring this up is it kind of illustrates the world that Cassandra is designed to work in, which is that if you do anything that requires you're spreading your data across many, many nodes. That gives you horizontal scalability. You can just keep adding nodes. But you then, as a trade-off, need to avoid doing things that require you to talk to all of those nodes. So as we dig into Cassandra, we'll find that Cassandra tries its level best to avoid that. So first of all, let's talk about replication. So how many of you use MySQL replication? Okay. So if you don't use replication, you better run MySQL first. So it's pretty simple, right? You have the bin log. The slave asks the master for the bin log. It makes a copy of it. Called the relay log. It then applies it. There's a nice example. We're being saved, so we set global read-only equals 1. So we have a read-only slave. This is how, sort of a canonical example of how MySQL replicates data. We'll talk about the layer a little bit, but this is the basic way that it works. And you may have it set up as multi-master in case you want to fail over, in which case it's reflected back. So how does Cassandra do replication? So Cassandra does replicate data because as you're spreading data across a bunch of nodes, if one of them dies, catches fire, is taken offline for maintenance, you would be missing a piece of your data. So the way that Cassandra works is it's a complete multi-master system. And so you've got a bunch of Cassandra nodes out there. You can go to any one of them and say, hey, I want to insert some data. And what that will do is it will become what's called a coordinator. And it will figure out where does the data that you're manipulating really belong. And it's going to go contact those servers. And so in this particular case, let's say that we're replicating 3 times. It just happens we've got to go to DB1, but we've also got to go to DB2 and DB3. It'll go ahead and take care of proxying the writes out to the other instances. So an interesting thing that's a difference from MySQL is we don't really have a log here. Remember that with MySQL, replication is all about the bin log, right? And we know that because if the bin log gets screwed up, replication no longer works. With Cassandra, it's like you talk to the node, and that node takes care of right then and there replicating the transaction to the other places that it belongs. So kind of an interesting and very different model. So you can decide how many replicas there are going to be when you create the key space. So the key space, remember, is kind of like a database in MySQL. And what you're going to do is you're going to go ahead and specify how the replication is to be done for that key space. Every table you create, if you use this definition, in this particular case, it's going to be replicated 3 times, and it's going to use a class called simple strategy, which is a standard replication algorithm for replicating data in a single site. Cassandra also has a variation on this called the network topology strategy, and it knows how to replicate data across sites. So, for example, it will know that, we need to get a couple copies on the site, and we'd like to get a copy or 2 out to another site. So it's kind of smart about where things are located. So this is something that you set when you create the key space. Once it's set, you can't change it. Cassandra partitions data, but before we get into that, it's useful to think about how MySQL partitions data. How many people have used partitioning in MySQL? Okay, that sounds about typical. So about 4 or 5 people. It's not a heavily used feature, but think about how it works. What it does is it breaks the tables up into pieces based on some partitioning strategy. A real common way to partition stuff is by dates. So, and the idea is that we'll break them up into a bunch of subtables, and it's very helpful, sort of if you have a lot of data in a table because it splits it up into pieces. It's also kind of nice because it helps you manage those tables. So for example, if you had a time series in MySQL, you could partition by day, for example. And then if you need to drop the last day, or the oldest day, you just can go drop that partition, and it's very quick. As opposed to having to scan the entire table to find where it's dropped. So that's MySQL partition. The big thing about it is it only works on a single node. It's within a single MySQL database. So Cassandra, though, is trying to solve a different problem, which is to spread data out over many, many nodes. And so Cassandra uses something called consistent hashing. And the idea behind consistent hashing is we are trying to break up a data set into a bunch of little pieces, which we are then going to assign to different nodes around the network. And so when you look at consistent hashing, it tends to have a picture of what's called a ring. And the way that this works, this is it took me a while to understand when I first hit this a few years ago. The idea is that you have a hashing strategy. It takes a key, like a username or something like that, and it converts it to a number. So Cassandra has several different hashing strategies. One is called murmur3, and it converts this, whatever key you have into a huge integer that starts very negative, goes to 0, and then goes to equally positive. So the idea is, in consistent hashing, you're going to break up that range of numbers, because the idea with a good hashing function, if you like to read Don Knuth or you're into algorithms, the idea with a hashing algorithm is it kind of splits the data evenly. No matter what the keys are, the next key will be just sort of randomly spread across the range. So if we break these things up into equal chunks of integer values, we will then get an equal distribution of data. And so Cassandra basically takes these hash tags and breaks them up into something that in the documentation they call a virtual node. But if you actually look inside Cassandra and you use it, it's called a token. So this is kind of confusing, but the basic idea is that let's say the smallest value, call that A, the next range is going to be called B. And what Cassandra does is it kind of randomly assigns them to all the nodes that it has. The actual number of partitions in the ring, or sort of tokens in the ring, is actually much larger than I'm showing here. It's in the hundreds or thousands. So, and they are just randomly sprinkled across these nodes. And so if I have, and its key corresponds to partition or to token A, it could be stored on, for example, DB1, DB2, or DB4. And the thing that's really important about this random distribution of data is that if one of these nodes dies, and this is where one of the strengths of consistent hashing, if you want to reconstruct that node, you basically have, that node has a certain ownership of data, and basically you can then go get it from a bunch of different locations on the net. You don't actually have to go to one place and make a copy, which would be slow because you would have to copy all the data from one single node. Instead, you have a bunch of nodes which can send you the data, use your network bandwidth effectively, and that allows you to reconstruct the node very quickly. So that's why Cassandra picked this algorithm. This algorithm, incidentally, was developed how many people have heard of Dynamo? So Dynamo is a database used developed by Amazon, and they were the first people that used this that I know of in a database. So Cassandra uses this. So how does it work then? You do an insert. There's your primary key ID. It's a big fat UUID. Run the hash function on it. That gets you your token. That's going to send you and Cassandra then knows that token, whatever token you get, it knows the 2, 3, 4 hosts that need to have that data, and it just sends it out. So that's how it works. So it's a pretty powerful way of distributing data. So looking a little bit deeper, so at this level, this is really different from MySQL. I mean, MySQL does not work this way. And in fact, if you go back and look at this picture, this explains why you can't do range chains in MySQL. This is why you can't take a primary key and say, hey, give me all the primary keys greater than this and less than that. The reason is very simple, that you've got a hashing function. It's sprinkling there's no order in the keys. They're just randomly distributed around all the nodes in your cluster. That's why Cassandra can't answer that question. And it's because they made this choice to try and solve this problem with horizontal scaling. So what is kind of interesting is that when you look at how Cassandra stores data, there's actually some surprising similarities to what you see in MySQL. So if you look inside MySQL, is everybody here familiar with the buffer pool? Okay, so most people. Well, the way the databases work is they can't do anything unless the data are in memory. So if you look at MySQL, you're using UnityDB, that's probably the engine most of you are using. When you do an insert, it goes into the buffer pool, so the page gets updated there, and then the changes get written out to something called the log buffer, and then at intervals, usually about a second or so, for most setups that I see, that's going to get written out to your transaction log. So the change that you made through that insert, within a second it hits in your transaction log, and then at periodic intervals, the pages inside the buffer pool that have been changed get flushed out in what's called a checkpoint. So they actually go down and they update the pages in storage so that your database has the fully changed data. This is how MySQL works. And the thing that's important about this is if you do a select, for example, in fact, if any operation you do in MySQL, it has to operate on data in memory. MySQL does not talk to storage directly. So what that means is you do the insert, as long as it doesn't have to go and read a bunch of stuff, for example, pull index pages so it can figure out how to update them, it's pretty quick. It will write them into the buffer pool, it'll put it in the log buffer, you then do a sequential write to the transaction log, and as most people I think know, if you're using rotating disk, sequential writes are very good, very fast. So similarly, if you do a select, if you just had done that insert, the page that you updated is sitting in the buffer pool, it comes back really fast. And this is why MySQL can be blindingly fast on select, because it's reading stuff straight out of the buffer pool. So Cassandra essentially does the same thing. And what happens though is it uses something called log structured storage. So this is kind of a storage innovation that's become fairly popular over the last few years. And the idea here is that with MySQL, what we tend to do is we make a change to the database, we're actually going to change that page and then write it out. In Cassandra, because they use log structured storage, they never change anything. They just write a series of appends. And if we want to delete something, we don't actually go and find the thing that needs to be deleted. We just write a record that says, hey, this key, the data associated with this key is gone now. It's called a tombstone. So in Cassandra, what we do is we write what's called a mutation. So, and it first gets written to the transaction log, so a lot like MySQL, we write the log, and then we write it to memory, something called a mem table. So you can think of this as being a bit like the buffer cache. So you've got an in-memory copy, and then eventually it gets flushed out to storage into something called a sorted string table, which is just like ordered keys, and so keys and values in sorted order. And so that's where the data are stored, and then sooner or later these things pile up because you just keep appending to them. So there's a process called compaction where eventually if you get more than a certain number of them, they reach a certain size, Cassandra will go in and it'll kind of reread them and then write new ones where, for example, all the deleted rows get thrown away, all the changes get collapsed into a single location. So this is kind of like, this is a different way of writing data out, but in a sense, it's the same thing that MySQL does. Keep stuff in memory, write to a transaction log to make sure we don't lose it. That's written sequentially. In fact, there's the sequential, we always write sequentially to the sorted string tables. They're sorted so that when you compact them again, it's a match merge. Again, sequential write. So a lot of the same ideas. One interesting question is, okay, if it works like this, does this mean selects are going to be really efficient? Because MySQL just gets them out of the buffer pool if it can. And this is where Cassandra has a kind of interesting quirk to it, which is that if you do a select and you give it a key, you'd think that it would go to the mem table, sort of the in-memory representation, and if it finds it there, it would call it good. And a lot of log structured systems do that. Cassandra actually doesn't. it actually still goes and looks at the sorted string tables. And this was a bit surprising to me because I spent some time for this part of the talk just debugging Cassandra, just to see what it did when it did select. And it turns out that what's going on there is Cassandra uses these timestamps, as you'll see in just a minute, to be able to resolve conflicts. And there are cases where the sorted string table can actually have a timestamp which is effectively later in time than what's in the nav table. So Cassandra, strangely enough, even though it has this structure, trying to do the same thing as MySQL, it still has to look at all the possible locations where the data can live. Yes?
Won't that massively slow down the reads?
It's very interesting. So Cassandra has very high read performance. And I was in the debugger and I was looking at this and I was actually really surprised. And then I went and looked and this is, yeah, I think it does. And in fact, if you look at MySQL performance, MySQL, if you have an optimized buffer pool, like you have a working set, fits in your buffer pool, MySQL is blindingly fast. My hypothesis is that in that case, MySQL is faster than Cassandra because Cassandra will have to do this. It does some optimizations, but it's kind of an interesting quirk, and it is because Cassandra's read efficiency is conflicting with this timestamp mechanism. Yes?
Well, wasn't that one of the complaints with the early versions, is that very fast writes, but the reads were really horrible, which has gotten better over time.
It has. So, for example, the SS tables have timestamps in them. There's various optimizations to avoid looking at things unnecessarily. Cassandra also uses something called a Bloom filter, which is used to, because Cassandra and a Bloom filter is kind of like an in-memory hash that answers the question, is this key possibly in the SS table that I'm looking at? So what they'll do is, and it's sort of like you hash the key a couple different, like 5 different ways or something like that. If the thing doesn't come up in the Bloom filter, then you don't have to look at that SS table. If the times, there's other optimizations, that's how they spit. I suspect that's how they got their speed ups. But this behavior is still there. I mean, I've seen it in the debugger in the latest version. Yes?
Why can't the data just be modified within the SS table?
Well, actually, that's a really good question. So the idea is here that we want to just have sequential writes everywhere. And that's a fundamental design decision. There's 2 reasons for it if you read the Cassandra documentation. One is that when we're writing data, if we're unrotating media, we're going to get sequential writes. These are blindingly fast. I mean, anybody who's run Sysbench, the difference between, I used to use SATA, 7,200 RPM SATA drives. The difference between random and sequential reads is that we're a third or more. Depends on your controller. Rates tend to do it better. So that's thing number 1. Thing number 2 is if you go and modify these things and you're running on cheap, I think the correct engineering term is cheap-ass SSDs, they're going to burn out because you'll get write amplification. Because what will happen is you need to change like a couple bytes in the table. SSDs are going to write the whole page and that's going to burn that page, right? So one of the things that Cassandra is optimized for is to run on cheap SSDs. So they made this design decision, so they have to append to the end. Does that make sense? Yeah.
Again, just to kind of follow up on the earlier question. So, what the diagram you're showing right here, what's the source, or is this assumed community and just common knowledge down to the sun?
I'm sorry, say that again?
Is this the fact that it's reading from memory and also asking the disk as a source system, is that typical? Is that community? Is it common knowledge at this point?
That it works this way?
Yeah.
The interesting thing is this is not in the documentation. If you go out and look at the code, yes, you'll see this. If you, they do talk. So one of the things that's kind of awkward about the Cassandra documentation is it's good from a user perspective, but it has very little information about what's actually going on inside. You will not read this. You will not actually see this in the Cassandra documentation. If you go to the mailing list and look at the source code, it's pretty obvious. Okay, so that's how Cassandra is storing data. And again, the interesting thing is, we saw that this hashing, the hashing algorithm is very, very different from the way that MySQL stores data. And that is because Cassandra is storing things across potentially hundreds of nodes. So you have to make very fundamentally different choices. the interesting thing is where we do see the similarities is once you get to a single Cassandra node and it's storing data, that's basically the same problem MySQL has, and that's why you sort of see some interesting similarities. So the last part is transactions and high availability. Big deal. I mean, nobody likes it when a database is gone because your app stopped, and if the app is important enough, your business stops. The big trade that Cassandra makes compared to MySQL and most other relational databases is data consistency is an application problem. You make decisions when you write your application about how much consistency do you need, what are your real HA requirements, and it's very different. So here's just a quick example, just a recollection of how MySQL handles transactions. And I tend to think of things in NoDB. Is anybody still running MySQL? It's okay, this is a safe place. Cool, okay, we have one brave. Thank you, sir.
Down the hall.
What's that?
That's the workroom down the hall.
Yeah, exactly. So generally speaking, here's how a transaction works in NoDB. And you do a begin, and what NoDB is, it basically freezes the world at that point. It does what's called MVCC, multi-version consistency control, where you basically see a consistent view, a more or less consistent view of the data starting at that point. And then you'll insert, that actually locks the updated rows, depending on your serialization level of data, lock other things, and then you commit, in it goes. It all happens atomically, so either both go in or they don't. MySQL, interestingly enough, if you recall, if you're old enough to remember, MySQL actually ignore that begin and commit nonsense, and just as soon as it sees the rows, or as soon as it sees the insert process, it's going to stick it in and calls it good. And if you have a failure in between, of course, you'd end up with one row inserted and not the other. So these are MySQL transactions. Let's look at Cassandra. So the question is, does Cassandra have transactions? And it's kind of well-but. So in some sense, the answer is no. And there's two really obvious examples. We saw this, talked about the partitioning and the fact that individual rows may be stored on different hosts. There's no transactions between those. You update one row here, you update another row there. Cassandra gives you no guarantee that those will be atomic. And that's because that's difficult to do and it will require coordination between these nodes. The Cassandra designers are trying to avoid that because it causes problems. The other interesting thing, and we'll discuss a case of this because we're not too far from the end, but show an example of this. Failed transactions on nodes can create partial writes. It's got some kind of interesting, kind of MyISAM-esque behavior where things can get a little bit messed up, and until you actually do something like run the equivalent of the moral equivalent of a repair table, Cassandra will leave a bit of a mess out there and not really tell you until later. On the other hand, you update a single row. Doesn't matter what you do in that row, it could be very large, it's atomic. Older versions of Cassandra apparently didn't have that behavior. There were numerous complaints. They fixed it, so single row updates are atomic as well as isolated. Moreover, when you do an update to a row, it commits the whole thing at once. It goes to it has a log, it has basically the same behavior that we expect in the NoDB log. When you say, when that thing goes back, goes in and Cassandra signals, I got you insert, it's committed. So they're durable. Now, one interesting thing is that Cassandra rows can be really, really big. So there is a kind of scope, if you will, for these single row transactions that could actually cover many, many rows that we think of in MySQL, but that's because of the way that Cassandra is organized. And you guys are totally keyed into that now, thanks to the earlier part of the talk. So an interesting question is, how does Cassandra handle locks? Because locks are bad in large distributed systems. And the reason is because if somebody wants to lock a row, they're going to actually have to communicate with other people who might be doing something to that row. Cassandra doesn't want to do that. So what they do is they actually use timestamps to serve the purpose of locks. So for example, if I insert a couple of values into the row, let's see, just reading an example again. Basically, you can actually check the write time. In fact, this is how you fish out these timestamps. You you go ahead and call this function write time, and you'll see in the rows there's actually a timestamp associated with the data. So, and basically, when a column is, any column that was updated at the same time will have the same timestamp. If it's updated a little later, it'll be a different timestamp. So the idea is that if something has the last timestamp, that's the real value of the row. If there were any question, there's no lock. In this particular case, there's no need to have anybody, kind of holding up a gate and saying, hey, you wait while you actually go and update the row. We're just going to give you guys a timestamp. Whoever has the latest timestamp, their value is going to win. That creates some kind of interesting behavior. Let's see, isolation, we already talked about that. The row updates are isolated, and then the updates can propagate out at different times. Won't go too deep into that. So let's talk about these conflicts. So Cassandra is completely multi-master in a way that is just not conceivable for people that, or for applications that run MySQL. You can be anywhere on the net, you can talk to any node, you can change any data, Cassandra will deal with it. And this is very powerful. So, and it's all based on these timestamps, because basically what we can do is, since there's a timestamp associated with the change of each cell, when you read the row and sort of merge all this data together, whichever timestamps are latest are the ones that win. So for example, if I do an update here, in this particular, I go ahead and do an update on this table sample, I set a couple fields, and then I have an update that sets one of the other fields. What will happen is the first update is basically one of those cells is going to get overridden, which is actually pretty reasonable. I mean, that's sort of that's actually how MySQL would work if things were properly updated. So the timestamps enable us to resolve these changes and just decide who's going to win. The bad part about this is you have no control over it. So if your clocks are not synchronized, people generate the wrong timestamp, weird things can happen. Imagine you had a system where its clock was off by 24 hours. I don't know if Cassandra would detect that, but what would happen is anything that system wrote would win over anything that had been written in the last 24 hours. So it's a little bit brittle. So the question is, how does MySQL do this? Because MySQL actually does try to solve the same problem. So how many people here have tried Galera or how many people are using Galera? Oh, okay, yeah, Roger. So yeah, not terrifically widely used. So MySQL, the Galera clusters try to solve the same problem, but in a very different way. What they do is they use something called group communication. So you have a bunch of nodes in a cluster. Any node can process a transaction, but when that transaction comes to commit, it gets shipped off. There's something called group communications. Group communications orders the transactions among all the nodes, gives them back, and then the nodes decide whether they should commit or not. And the idea is everybody's going to commit the transactions in the same order. And they're also going to have a special feature, which is they're going to prevent conflicting transactions from occurring. So if T1, for example, changes one row and T2 comes after and tries to change the same row, Galera will just toss it out. And each of the Galera nodes will, through this process of certification, come to the same decision. T1 updated one row, T2 tried to change it, so out it goes. So the question is Cassandra like this? Well, the answer is no, it's not, in two ways. So one, Galera is fully absent. So the standard transaction model, it does not permit conflicts. It works just like a lock, except that if things do conflict, they get tossed out. Normally in locks, in a single database, one guy waits and then he goes later. And what Galera would do is, going back to that same example, if we had this update on one node and then the update on another node, maybe just they got in a little later, Galera would toss the second one completely. So this algorithm gives very, very different results from Cassandra because of the transaction symbols. There's another way, though, the more fundamental way that this is different. This requires communication between all the nodes in the cluster. Cassandra doesn't want to do that because communication among dozens and hundreds of nodes is bad. It's slow. It's dependent on it puts you in thrall to the slowest database. So, yeah. Cassandra, it's very hard to do. So what you're going to need, so if you're going to, so one of the, incrementing a counter is one of the classic problems in distributed systems because it requires everybody who uses that counter to communicate.
What counters don't use?
Yeah.
How accurate do you want the counters to be?
Yeah.
Is the real question.
What did you say?
Yeah.
How accurate?
Oh, how accurate?
Yeah.
If you can have counters that are off.
Yeah, so the timestamps, they're sort of making it's kind of loosey-goosey. The assumption is everybody's clocks are pretty well synchronized. That's good enough for ordering in most cases. And imagine if you're doing a user profile. I mean, this is getting kind of arcane. You're doing a user profile, there's rarely a conflict. It's always typically done by one person, since every change gets a later timestamp because it's coming from one place or one user, there's not a problem. So it's a really, it's an interesting case, and you just get used to building these horizontally scaled systems where the standard advice is, hey, don't do that. Think of a different way of getting that order you're looking for. So Cassandra also has another really, really interesting property. This is sort of the final area of differences. So there isn't a notion of failover. And this is not just a difference between MySQL and Cassandra, it's a difference between Cassandra and many other types of distributed databases. If Cassandra has 100 nodes and 99 fail, Cassandra actually continues to work. The one node that is there can still continue to work and take, it can take reads, it can take writes. Now, the applications may stop because they may decide that's not enough data to do their work. There are not enough replicas for them to feel comfortable getting a good answer. But basically, when Cassandra, issues a write, if one of the nodes is not there, fine. It just sends it to the instances that are live, and then it does something called hinted handoff, where the coordinator just remembers, hey, there was somebody I needed to talk to and tell him about a change. He wasn't there, so I'm going to wait. And if that node comes back, I will send it the list of changes that it missed. That's basically how Cassandra handles it. So the question then is, how do you decide when you're losing consistency, when there's just not enough replicas to feel safe about what you're doing? Well, the applications define this. So applications say, how many copies do I need to have to be safe? So here's an example. And there's commands in SQL, like consistency all means, hey, if I'm set at replication level 3, I gotta see changes go to all 3 replicas successfully, or I want to bomb out. So here's an example. Set consistency all. In this particular example, I had killed one of the nodes. Go ahead and do my update. You get, at least in 207, you got this this email, or this error message. Error message, can't do the request because you were missing a node. I could go ahead though, and I could do a select. And similarly, it would bomb out because it actually wanted to see results from all 3 replicas to make sure they were consistent. What I can do though is I can set the consistency of what's called quorum, which means, hey, if I've got a majority of my replicas that let my transactions go through, I do the update and it works. Cassandra will also allow you to do just one, update to one. There's a completely sort of negligent setting, which just says, hey, if you got the request in any form, you're good, signal the application. If it's data you don't really care about, that works. Yeah.
So let's say you're replicating 3 times and the node goes down. How long can that node be down before you bring it back up and it proceeds to give it the data?
Great question. 3 hours is the default for a hinted handoff. It doesn't.
It's not amount. It's just time.
It's just time. It's bounded by time. So, and it's not like MySQL. We actually had a customer for our product a while back had a failure where they were offline for 2 months and they had neglected to install monitoring. So when they called us, it had been like 58 days. Fortunately, they had logs. We were able to kind of get them. And with bin logs, if you don't delete them, it doesn't matter how long you're offline. The bin log has the record of what has to be applied, and then you restart replication. As long as the logs haven't been aged out, it continues. Cassandra is not like that. And that does create some interesting issues, like what happens when you get these failed writes. So this hinted handoff mechanism, what will happen is if the guy the node that missed the write comes back soon enough, The coordinator will notice that it's there, give the rights back, and everything will be good. Cassandra has another interesting mechanism called read repair. So if you're doing reads and going to multiple replicas, Cassandra will notice that one of the replicas who are expected to find the data either doesn't have the data or it's out of date. And what it'll do is it'll then copy it from one of the others. And it does this silently in the background. As long as you're checking your data, it will basically kind of get back, stochastically, if you will, get back into consistency again. But there's no guarantee. I mean, it's just sort of a statistical thing. So in the worst case, you have to run. In fact, my understanding is that if you're running Cassandra at scale, you're going to run node repair. And that's kind of like, God forbid, it's like repair table. What this is saying is, let's go scan this node, check the other replicas, and sort of explicitly find and fix the inconsistencies. Node repair is a standard operation in large Cassandra installations.
But it doesn't lock the table.
No. Again, no locks in the system. So it doesn't do that. It doesn't it doesn't hang your system. But what you basically have is in Cassandra, it's a bit like my ISAM on a grand scale, where things are just probably in any large system in Cassandra, my guess would be things are always a little messed up. But that's true of distributed systems in general. So I can't really fault Cassandra in making a decision that is a fair decision based on the problem that they're solving. So that's kind of it. I've sort of scratched the surface of this, and I hope this is interesting. This is something that personally interests me. I was kind of like the kid who used to take the machine tools apart in fact, once when the power saw was plugged in, that didn't end well. So I like understanding how they work inside. But based on this talk, I want to give you an example. I didn't put a slide together for it, but I think I can illustrate pretty simply the difference between these two systems and like the kind of applications that they're really good for. So imagine that you are doing marketing automation. One of the customers I work with quite a bit is a company called Marketo. And they do marketing automation. The idea is that you open some email, some spam email you get, and what's going to happen is you'll touch that link, you'll touch a link in it, you'll sometimes see this MKTO thing kind of flash up, and you can see the URL. What's happened is they just made an update in a MySQL database somewhere. And what they're doing is they have a bunch of customers and they're collecting the exact results of the of the marketing campaign, like who touched the email, how long did they have it open for, did they go to some other website afterwards? And there's a bunch of related reference data. So companies, marketing campaigns that are all directly related to that information, and you want to be consistent because they're going to run reports and they're going to use that to identify customers. They're going to do things like value who are the customers that are most important to us. The consistency of the data and the relationships between the data are very important. This is a really great example to run inside MySQL. Another thing is it's human generated. So even though they generate a lot of spam, a lot of emails, the amount of data that they generate for a user, I actually looked at this a couple of years ago, and it was about a terabyte. And MySQL has no problem with a terabyte. It has no problem actually up to 5 or 6 terabytes. So that's a great example of where relational databases with indexing, with the ability to maintain relationships, with the ability to query across those relationships, it's a very, very good fit. Here's another example though. Imagine you're doing a chat service for mobile phones. It runs worldwide. You have potentially millions of users and they have chats. And each user wants to join the chat. They want to see what has been done in that chat. They want to add stuff to that chat. This is something where the data that this generates, first of all, is unbounded. Because it's just sort of like, how long do you keep the chats around? And moreover, the amount of information you could get, you could actually have one of these systems have 1 billion users for it. That is the chat problem that Facebook has. So this data model, where you can imagine each chat gets a partition key, and then you take those wide rows and you use that to represent each additional message in the chat up to 2 billion. That's a great use case for a database like Cassandra. So and I think you can see that this, sort of the designers and the systems have made different choices that allow them to solve these problems really well. So if you want to learn more about Cassandra, just some advice here. It's really different. I think that's the big lesson. It looks like SQL, it's not. It's really different. So you have to, you can't port now a MySQL app to Cassandra. You're going to rewrite because you're really developing a different application. Consistency model is also really interesting. You're now thinking, what is the application comfortable with, and the application specifies that. There's a bunch of storage internals. I've just touched the surface. I mentioned all of these things, but there's actually, running MySQL at scale, you want to know how it works inside. Unfortunately, it is not as well documented by far as MySQL is, and administration is non-trivial. There are some pretty important decisions. I'm not an expert on this, but I can tell just by looking at the files that there are things in for example, in Cassandra.yaml, if you mess them up, you will be very, very unhappy. You get 100 nodes. For example, there are settings, for example, that once you, like a partitioning algorithm, once you've set that, that's the life of that data. If you don't like the way that the hashing is happening and you want to use a different algorithm, you set up a new cluster, you copy all your data over there. If you're in the hundreds of nodes, that could be bad. So, what should you do? Cassandra is actually pretty popular. That's 2013, so behind MongoDB, but I think it's more interesting, so I would go for Cassandra. As we went through this, just sort of what we liked. SQL and the tables, they make it easy to get started, but they can be sort of tricky as well. The built-in high availability, this is a really, really great feature. In fact, if I had to point to one place where relational databases just don't do the job anymore, it's HA. And I say that as somebody who's built an HA product for years. NoSQL databases just do this out of the box. That's the way it should be. And then the scaling model is great. I mean, this will handle a level of data that MySQL can only dream of. On the other hand, as I said, don't try and port your application. Really think about it. Cassandra is also, this is an important point, Cassandra is evolving very quickly. So one of the difficulties in learning Cassandra is that, for example, there's inconsistencies in the nomenclature. Because they've changed their minds over years, they now use different terms, so you'll need to be a little careful about that. There's lots of good reading about this. Cassandra has good user docs. As I mentioned, they don't explain what's going on inside. Some of the things that purport to explain what's going on inside, like the hashing, are a little bit misleading. There's some very, very good presentations out there, just Google them. Blogs, the eBay Tech blog has some interesting stuff. PlanetCassandra.org, that one's not so good. I think that's kind of propagandistic. Yes?
I have to put in a pitch for the Cassandra user mailing list.
Oh, yes. That's where you go. Yeah, exactly. It's a really good mailing list. In fact, that's why I confirmed that read behavior, because I was like, crap, right? That can't really be happening. And I Googled it, and sure enough, there was an email message that said, yes, this is exactly what's happening. Yeah, very good. And don't forget the source. It's really not that bad. It takes 10 minutes to pull it off Git, build it. I'm a Java guy. Maybe not everybody here is a Java guy. It's actually not that easy. They're not that hard to follow what it's doing. So you can look at the source if you're really into that. And I think that's it. So thank you very much.